Originally, the elements on the periodic table were arranged according to mass, but atomic mass isn't an element's defining characteristic. To see why, we need to look at what's inside the atom and what effect that has on its chemistry, on the way it interacts with other atoms. Atoms are composed of three different types of particles. The proton, which is positively charged, and the neutron, which has no electric charge, are both inside the nucleus. Now, they have both about the same mass, which is around 1800 times larger than the mass of the negatively charged electron. Electrons are so much lighter than protons or neutrons that we can effectively forget about them when we're calculating atomic mass. Because electrons are so light, it means that they respond almost instantly to changes in the electric field nearby. That means that if another atom is coming towards them, they might respond to the positive charge on the other atom's nucleus by forming a bond between the two atoms. Or they might respond to the electric field of the electrons surrounding that nucleus, and the electron-electron repulsion will affect the molecular geometry. Of course, the biggest, closest influence on an electron's behavior within an atom is its own atomic nucleus. The charge on the atomic nucleus is determined by the number of protons inside the nucleus, not the number of neutrons. The nuclear charge determines the electron configuration, which in turn determines how the atom reacts to other atoms, which inspired chemists to arrange the elements according to their periodic trends in reactivity. So that's why mass isn't the defining characteristic of an element, because we can change the mass by adding or subtracting neutrons without changing the nuclear charge. But as soon as we change the number of protons, we change the charge in the nucleus, and so we change its chemical properties, which couldn't be the case if the atom was the same element. Therefore, the number of protons is the defining characteristic of an element. Two atoms with the same number of protons are the same element. If they have different numbers of neutrons, they're called isotopes of the same element. But if two atoms of the same element have different masses, how do they get that one number to use for the atomic mass that shows up on the periodic table? The mass of one atom is on the order of a few 10 to the negative 27ths of a kilogram. So to avoid writing times 10 to the negative 27 any more than we have to, chemists use a unit of measure called the atomic mass units, or AMU. One AMU is equal to 1/12 the mass of a carbon-12 atom, or very nearly the average mass of a proton and a neutron. Atomic mass is therefore approximately equal to the sum of the atom's protons and neutrons. Carbon-12 has 6 protons and 6 neutrons, and its atomic mass is 12 AMU. Conveniently, this also means that the mass of 1 mole of carbon-12 is 12 grams. That's why we can use atomic mass on the periodic table as a conversion factor between grams and moles. But again, the periodic table lists the atomic mass of carbon as 12.011, not 12 AMU, or grams per mole. While carbon-12 is the most stable carbon isotope, there are others that are naturally occurring and in sufficient quantity that we have to count them in the average. Carbon-13 and carbon-14 are both unstable. They're radioactive and they decay into other elements, but they're also being replenished constantly and at a steady state. So in any given sample of carbon, you're likely to have some carbon-12, some carbon-13, and some carbon-14. And how much you have of each is what's called its natural abundance. 98.9% of all the carbon atoms you're likely to come across are carbon-12. The other 1.1% are carbon-13, except every trillion atoms or so you're going to have one carbon-14. So if every mole of carbon contains 0.989 moles of carbon-12 and 0.011 moles of carbon-13, we can calculate the mass of our average mole as 12 times 0.989 plus 13 times 0.011, which gives us 12.011, just like we see on the periodic table. Let's try one more example. Uranium has 3 isotopes with enough natural abundance to affect the atomic mass. U-238 is the most abundant and represents 99.274% of all uranium atoms on Earth. Uranium-235 is a distant second at 0.72%. Uranium-235 is the fissile isotope. A sample with a uranium-235 concentration above 0.72% is called enriched, and that gets used in nuclear power plants or nuclear weapons. And a lower proportion is called depleted, which can be used for a bunch of other different applications. Uranium-233 is also in the mix, but it's again significantly lower at just 0.005%. The overall atomic mass is the weighted average of these three isotopes, or as we calculate it, 237.98 grams per mole, which still isn't quite the same as what's written on the periodic table. There's an interesting reason why that is, but unfortunately that story is going to have to wait until we reach nuclear chemistry later this fall.